December 1st, 2021, Kuusamo, Finland. A Boeing 737 carrying 6 crew accelerates down a snow-covered runway in the dark. Both pilots feel something is wrong. The acceleration is slow, the cadence is off, but neither can identify why. They don't abort. The aircraft lifts off with 400 meters of runway left, climbing at barely 600 feet per minute. At 250 feet, the first officer finally says it. "We need more power." The engines have been running at 70%. Run-up power, not takeoff power. The one button that was supposed to set the correct thrust was never pressed, and the one cross-check that was supposed to catch it was interrupted by a radio call that lasted 5 seconds. 32 similar events have been recorded worldwide in just 5 years. No system exists to warn pilots when it happens, not yet. To understand how a routine departure nearly became a catastrophe, you have to go back to earlier that same day, at London Stansted Airport in the United Kingdom. The two pilots had both been off duty the day before, but knowing they were scheduled to fly to Kuusamo, a small airport in northern Finland, just 10 nautical miles from the Russian border, and knowing it would be December, both had spent part of their free day at home, reviewing winter operations procedures. That might sound unusual, but it is not. Winter ops is one of the most complicated things pilots do. Snow and ice affect nearly every phase of flight. Landing distance calculations, braking performance, de-icing holdover times, flap sequences, engine inspections, and the way aircraft are configured before departure. Pilots based at London airports can go months without encountering real winter conditions. When it finally arrives, preparation is everything. At around 9:15 in the morning, the two pilots met in the crew room at Stansted and started working through their briefing material. The weather along the route was reasonable, but Kuusamo was as expected. Light northeast wind, continuous light snowfall, temperature -8 degrees Celsius, visibility between 6 and 8 kilometers. Cold and Scandinavian, but not extreme. One procedural note stood out. Kuusamo Airport was scheduled to transition from air traffic control to a flight information service around the time of their arrival. This meant the tower could not issue direct clearances, only provide information. Aircraft departing from Finnish FIS airports were required to report which direction they intended to turn after takeoff. This was a well-established local procedure, familiar to airlines that regularly operated there. Less familiar to this Jet 2 crew, who had never flown into Kuusamo before. The captain was 44 years old, with about 7,450 total hours, including 3,300 on the Boeing 737. The first officer was 41, with 4,500 hours, and roughly 2,400 on type. Both were experienced in general terms, but neither had significant real-world winter ops experience. The captain had some from a previous airline. The first officer's only exposure had been in the simulator. Still, both felt well prepared. They walked out to their aircraft, a 5-year-old Boeing 737-800. Registration, Golf Juliet Zulu Hotel Lima. 2 CFM56 engines, in excellent mechanical condition. The captain would fly the outbound leg. The first officer would fly them home. 4 cabin crew greeted the passengers as they boarded. At around 10:15 local time, the 737 departed Stansted and climbed north toward Scandinavia. The outbound flight was uneventful. During the cruise, with the passengers settled and the workload low, the pilots used the time to walk through the winter departure procedures they would need at Kuusamo. Winter ops changes almost everything about a departure. The flaps, which are normally extended at the gate, are left retracted until the holding point because they are not protected by anti-icing fluid. The engines need to be inspected for ice and may require a run-up on the runway. The performance calculations use different assumptions for braking and acceleration on contaminated surfaces. The holdover time for the de-icing fluid is limited by the rate of snowfall and the temperature, creating a countdown from the moment the fluid is applied to the moment the aircraft must be airborne. Everything tells you to hurry up. The holdover clock, the schedule, the cold, but the procedures demand that you slow down. There are more steps, more checks, more ways to make a mistake. And one procedure in particular sat at the center of what was about to happen: the pre-departure engine run-up. The aircraft landed normally in Kuusamo on runway 30 and taxied to the stand. Outside the windows, the Finnish winter was exactly as advertised. A flat, white landscape under low gray skies. Light snow falling steadily. The airport buildings dusted with it. The temperature gauge in the cockpit read -8. Ground crews in heavy parkas moved around the ramp, their breath visible in the cold air. The passengers disembarked into the terminal, glad to be on the ground after the short hop from London. The return flight would carry only the 2 pilots and 4 cabin crew. No passengers, no revenue cargo. An empty aircraft heading home. The takeoff weight would be roughly 52,000 kilos, about 15 to 20 tons lighter than a normal revenue flight. The pilots entered the current conditions into their electronic flight bags and ran the performance calculations. Temperature -8, wind from 040 at 5 knots, runway covered in 3 millimeters of dry snow, runway condition code 4, braking action medium to good. The software returned a takeoff thrust of 89% N1 and speeds of V1 at 93 knots, rotation at 122, V2 at 131, flaps 5. The V1 was unusually low, close to VMCG, the minimum control speed on the ground, a consequence of the slippery runway and very light weight. This meant the aircraft would be committed to fly very early in the roll. Any problem after V1 would have to be solved in the air. The pilots chose runway 12 for departure. Taxiway Alpha was right at the runway 12 threshold, eliminating the need to backtrack 2,500 meters through the snow. It also kept the taxi short, important for the de-icing holdover window. The first officer briefed the departure. He covered the run-up procedure, the delayed flap extension, the performance numbers. And he briefed one specific contingency. If the aircraft started sliding on the icy surface during the run-up, they should simply release the brakes and begin the takeoff roll immediately. The captain agreed. Let it go if the aircraft starts moving. It was a sensible plan, the kind of thing experienced pilots brief all the time in winter conditions. A small decision that both men would forget within minutes of making it. But that phrase, "let it go," was about to become the most important thing said in this cockpit. To understand why what happened next was so dangerous, you need to know how an engine run-up works on the 737. In winter conditions, ice can build up on the fan blades during taxi, even if the blades were clean at the gate. If that ice breaks loose during the takeoff roll, it can damage the engine. So before departing from a contaminated runway when the temperature is below 3 degrees with visible moisture, crews perform a run-up. The captain lines up on the runway and hands control to the first officer, who is pilot flying. The first officer holds the aircraft on the toe brakes, advances the thrust to 40%, lets the engine stabilize, then pushes to 70% and holds it there for about 30 seconds. If the vibration readings stay normal, the first officer then releases the brakes, presses the TOGA button, takeoff go around, and calls set takeoff thrust. That button is the dividing line between a run-up and a takeoff. It commands the autothrottle to advance the engines from 70% to the calculated takeoff power, in this case, 89% N1. It also activates the flight directors and engages the takeoff mode on the flight mode annunciator. Without it, the engines stay at 70%. And here is the critical detail. 70% N1 is not 70% of the takeoff thrust. Jet engine output increases almost exponentially at higher power settings. At 70% N1, the aircraft produces roughly 53% of the actual thrust it needs for takeoff, about what you would get from a single engine. Remember that number. The other half of this system is the captain's cross-check. Once the first officer presses TOGA and calls set takeoff thrust, the captain verifies that the N1 gauges match the green takeoff bugs on the engine display, then takes control of the thrust levers. This is the last barrier in the system. If the TOGA button is missed and the captain does not catch it, there is nothing else, no alarm, no warning, no automated system, to tell the crew they are attempting to fly on half the power they need. If you're enjoying this video, please take a moment to subscribe and hit that notification bell. It helps us bring you more stories like this one. The de-icing was completed. The cabin crew took their seats. Both engines were started, and the captain taxied the short distance to taxiway Alpha, lined up on runway 12, and handed control to the first officer. The landing lights illuminated the snow-covered surface ahead, disappearing into the December darkness. The captain reported to the FIS officer that they were lined up and ready. Before the run-up began, the captain decided he wanted the secondary engine display visible on the lower screen, so he could monitor the instruments during the 30-second hold. This meant he had pressed the M, F, D button to bring up the display, and he would need to press it twice more once the takeoff roll started, while simultaneously starting his elapsed time clock with his other hand. A small, self-imposed task load at the worst possible moment. The FIS officer cleared the runway and advised no traffic, but she had noticed something. The crew had never reported which direction they intended to turn after takeoff. Their departure clearance called for a right turn. She held the thought, waiting for the right moment to ask. The first officer advanced the thrust to 40%. The engines stabilized. He then pushed to 70%, holding the aircraft on the toe brakes as the CFM56 engines spooled up and the whole airframe shook with the power. And then the aircraft lurched forward. It began to move. What actually happened was simple. The first officer was not pressing the toe brakes hard enough. The 737 was not sliding on ice. It was rolling forward against insufficient braking force. But in the right seat, with the aircraft shaking at 70% and snowbanks flanking the narrow, cleared runway surface, it felt exactly like a slide. The first officer pushed rudder to correct a slight yaw, acutely aware of how close the edges were. He called out to the captain, "It's sliding." The captain responded with the words they had briefed, "Let it go." The first officer released the brakes. The aircraft began to accelerate down the runway, but in the startle of the unexpected movement, the yaw correction, the proximity of the snowbanks, the rush to get the aircraft tracking straight, he never pressed the TOGA button. He never called set takeoff thrust. His attention went entirely to the rudder pedals and the view outside the windscreen. The one action that would have set the correct power was lost in the scramble. The engine stayed at 70%, 53% of the thrust they needed. At that same moment, the FIS officer transmitted, "Jet 22152, confirm you would be turning right off the departure." The captain heard the call. He paused, processed the question. This was the turn direction he had never reported, the local procedure he was not fully familiar with, and keyed the radio. Affirm, 5 seconds, maybe 6. It was a perfectly reasonable exchange. The FIS officer was doing her job, the captain was doing his. But those 5 seconds fell across the only window in the entire departure sequence where the missing TOGA press could have been caught. By the time the captain looked back down at his instruments, the aircraft had already passed 53 knots and was accelerating toward the 80-knot cross-check. He had not verified the thrust. He had not checked the N1 bugs. He had not looked at the flight mode annunciator. The captain's cross-check, the last human barrier in the entire system, had been consumed by a 5-second radio exchange about which direction to turn. Outside, the runway lights streaked past in the darkness, the snow swirling in the wake of the engines. Inside the cockpit, neither pilot knew they were flying on half power. Neither pilot was now monitoring the engine instruments. The N1 gauges showed 70%, well short of the 89% takeoff bugs marked in green on both displays. The flight mode annunciator, a strip of text at the top of both primary flight displays that shows the current autopilot and autothrottle modes, displayed ARM and ELEV in white instead of the green TOGA and N1 annunciations that should have appeared if the button had been pressed. The flight directors were inactive. The crosshair symbols that normally guide the pilot's pitch and roll commands during takeoff were absent from both attitude indicators. Any one of these indications, noticed by either pilot at any point during the roll, would have revealed the problem instantly. All three were visible, continuously, on the instrument panel directly in front of both crew members for the entire duration of the takeoff. None were seen. The 737 accelerated at 2.25 knots per second. A normal takeoff at this weight would be closer to 4. The aircraft was producing only 53% of its required takeoff thrust, the equivalent of flying on a single engine. And every meter of runway it consumed was a meter it could not get back. Both pilots felt something was wrong. The roll seemed slow. The rhythm was off. The cadence of the speed callouts felt stretched, as though the numbers on the airspeed tape were reluctant to move. The captain attributed it to the snow on the runway, creating extra drag. The first officer felt the aircraft was heavy and sluggish, even though it was 15 tons lighter than a typical revenue flight. But neither could name the specific problem. and neither felt certain enough to reject the takeoff. This is not unusual. Research has consistently shown that humans are remarkably poor at perceiving differences in acceleration during takeoff. We judge speed visually, by watching the runway markings pass beneath us, by the lights rushing by in the periphery, but acceleration itself is processed through the vestibular system, which is simply not calibrated to detect the difference between 4 knots per second and 2. Pilots who perform hundreds of takeoffs a year, each slightly different in weight, wind, and surface condition, cannot reliably tell the difference between normal and dangerously slow acceleration by feel alone. The unease was real. The ability to diagnose it was not. 80 knots. The captain calls it. Cross-checked. The runway is being consumed behind them at roughly 200 meters every 10 seconds, and they are not even halfway through the roll. 93 knots. V1. The captain calls it. They are now committed. There is no safe way to stop on this contaminated runway. Whatever happens from this point will happen in the air. 122 knots. Rotate. The captain calls it. 400 meters of runway remain. 1,500 feet of asphalt between them and the snowbanks at the far end. The first officer pulls back on the column. The 737 lifts off, slowly, reluctantly, nose rising through the snow-filled darkness, as though the air itself is pushing back. At 70% N1, both engines together are producing only 53% of the thrust calculated for this takeoff, roughly the same as a single engine at full power. The first officer pitches toward the standard 15-degree takeoff attitude, but the speed stops accelerating around V2, 131 knots. It hovers there, refusing to build. He lowers the nose to 10 degrees. The climb rate settles at 600 feet per minute, barely half of normal. Below them, the dark, finished terrain offers no margin. Ahead, there is nothing but blackness and the slowly rising altimeter. The sensation is unmistakable now. This aircraft is flying the way it would on a single engine, without the yaw, because that is essentially what it is doing. He looks down at his primary flight display and sees no vertical guidance from the flight directors. Because TOGA was never pressed, the flight directors were never activated. The flight mode annunciator shows ARM and ELIV, where it should show TOGA and N1. The connection forms. No TOGA, no flight directors, no commanded thrust. The button was never pressed. The captain retracts the gear. Still no acceleration. The aircraft hangs in the cold air at 200 feet, climbing at a rate that would take nearly 9 minutes to reach 1,000 feet. The first officer says what the instruments have been showing since the start of the roll. We need more power. The captain looks at the engine display. 70%. The green bug sitting at 89, untouched. He immediately advances the thrust levers. The engines respond. The difference is instant, dramatic, a surge of acceleration that confirms just how far below the correct setting they had been. At 250 feet above the frozen Finnish landscape, the 737 finally climbs the way it was designed to. They continue the departure without further incident. At 2,400 feet, the captain reduces to climb thrust. At 3,900 feet, they retract flaps and the autopilot engages. The aircraft climbs to flight level 400 and proceeds to London Stansted. All 6 crew members land safely. No one is hurt. The aircraft is undamaged. The cockpit voice recording, which would have captured every word from Let It Go to We Need More Power, is overwritten during the 2-hour flight home. New regulations are being implemented to extend CVR recording beyond 2 hours for exactly this reason. The UK Air Accidents Investigation Branch led the investigation, delegated by Finland's Safety Investigation Authority. The AAIB analyzed the flight data recorder and quick access recorder data, interviewed both pilots, and examined the procedural and systemic factors surrounding the event. Their findings were clear. The thrust was not set correctly, because the TOGA button was never pressed. The button was not pressed because the first officer was startled by the aircraft moving during the run-up and shifted all his attention to directional control. The aircraft moved because the first officer applied insufficient brake pressure, not a slide on ice, but simply not enough force on the toe brakes to hold a 737 at 70% power. The captain's thrust verification, the last human barrier, was missed because he was responding to the FIS officer's radio call during the first seconds of the roll. and both pilots sensed the abnormal acceleration throughout the entire takeoff, but could not identify the cause, attributing it to the runway contamination rather than a thrust setting error. The AAIB noted that this failure to perceive abnormal acceleration was consistent with every similar event they had investigated. It was not a failure of this crew, but a fundamental limitation of human physiology that no amount of training can fully overcome. The AAIB then placed this incident inside a pattern that should concern the entire industry. Since mid-2017, investigators had compiled a non-exhaustive list of 32 similar takeoff performance events worldwide. Different airlines, different aircraft types, different root causes. Some involved wrong temperatures entered into performance computers. Others involved incorrect runway intersection entries that gave the crew less distance than they calculated for. Others, like this one, involved missed thrust settings. In 2017, another Boeing 737-800 had taken off from Belfast with 189 passengers on board and lifted off just 29 meters past the end of the runway, taking out an approach light because of an incorrect temperature entry. No one was hurt, but the AAIB had made a safety recommendation after that event, calling for a takeoff acceleration monitoring system. 5 years later, no such system existed, and the events kept happening. The circumstances differed each time. The outcome was the same. The aircraft took off with insufficient performance, and the human checks in place failed to prevent it. The problem is fundamental. Humans cannot reliably detect abnormal acceleration during takeoff. The cross-checks that exist all depend on a pilot looking at the correct instrument at the correct time during the most task-saturated phase of flight. If anything disrupts that scan, a startle, a radio call, a yaw correction, the barrier collapses, and there is currently no technological backup. The AAIB issued 2 safety recommendations. First, aviation authorities worldwide must develop technical specifications and standards for a takeoff acceleration monitoring system, a system that compares actual acceleration against expected acceleration and alerts the crew at low speed, giving them time to safely reject the takeoff. The technology is not complex. It needs to measure what the aircraft is doing against what it should be doing. Second, all airlines should implement detection algorithms in their flight data monitoring programs to identify precursors to these events, so the true scale of the problem can be measured. Jet2 responded with immediate action. They added run-up scenarios with deliberate distractions to recurrent simulator training. They updated procedures to emphasize brake application in the TOGA button press. Their pilots were reminded of the Finnish FIS reporting requirements, and the Kuusamo FIS officers were instructed to avoid non-essential transmissions during takeoff and initial climb. These are good steps, but they are human steps: training, awareness, procedure refinements. They address this crew's specific failures. They do not close the systemic gap that allowed those failures to propagate for 2,500 meters of runway with no automated warning. A takeoff acceleration monitoring system would have caught the problem in the first few hundred meters, well before V1, well before the point of no return. The technology to build it is straightforward. It needs to compare actual acceleration against expected acceleration and trigger an alert when the difference exceeds a threshold. It does not require complex performance inputs or weather data. It just needs to measure what the aircraft is doing. Every modern aircraft already has the sensors to do this. The software does not exist yet. After 32 events in 5 years, including one that took out an approach light with 189 passengers on board, the question is no longer whether this system is needed. The question is why it has not been built. On a dark December evening in Finland, a captain told his first officer, "Let it go." The instruction was correct. The plan was sound. But when the aircraft lurched forward and the first officer released the brakes and the startle erased the next step from his sequence, letting it go meant letting go of the one action that separated a safe departure from a near disaster. The TOGA button was never pressed. The cross-check was never made. And for 2,500 meters of Finnish runway, 6 people accelerated into the darkness on 53% of the power they needed, with every human barrier behind them and nothing ahead but 400 meters of snow and the hope that the math would hold. If you found this video valuable, please like and subscribe. Sharing these stories is how we make sure the lessons aren't forgotten. And if you want to see what happens when an aircraft's own instruments betray its crew, showing a perfect approach while flying them straight into an invisible mountain, that story is right here.